Good afternoon, everyone, and we welcome you for this another technical webinar series from SimScale. I am Ajit, and I work as a senior solutions engineer at SimScale, and I'll be hosting this webinar for the attendees today. Once again, welcome to everyone today. And today's key topic of discussion is how to optimize filters and filtration systems using CFD. We'll be looking at a few challenges that we hear from our customers and see how SimScale can be effectively used to optimize filters, both in terms of the design changes and also a little bit about how we can increase the operational efficiency if the design iterations are done, how we can use simulations to accelerate the design process in general as well. And that covers most of the agenda for today. And we have two interesting case studies that exactly discusses about how the operational efficiency can be increased and how CFD in general can be used to improve the efficiency of filters and filtration systems. And the case studies will cover two major applications, one with an air filter, it's for an air intake for turbines, and the second one is a water filter, mostly used as strainers before the main water flow system or filtration system is being connected to it. And at the end, we'll also have a question and answer section. So please feel free to actually leave your questions in your questions box. And you can also post that in the chat, and we'll be monitoring that and picking up the questions at the end of the session and answer them. Yeah. Great. Before jumping into the main part here, let's quickly discuss or describe how SimScale works and how is it different from the available on-premise tools in the market. When you talk about SimScale, it is a completely cloud-native simulation solutions. And it means that you don't need to actually install any software locally on your hardware. You don't even need a hardware to run complex simulations. It's a completely cloud-native SaaS system with instant access everywhere, anywhere, and anytime from within a simple browser and an internet connection. This means you also don't need the IT maintenance, updating the software, or no VPN connection to access this simulation data or run simulations itself. The next critical point about SimScale is we have one platform that supports broad physics. So unlike other tools, there is no disconnected tools in silos. A single platform where you need to log in and you can run through many different physics in the same hood. Something that we usually hear from our customers and we are proud of is the real-time collaboration and the support that we provide to our customers. Within SimScale, you're not just looking at a simulation platform, but also a collaboration platform as well. You'll be able to share and edit projects real-time, like what you see in a Google Docs style. So this will enable parallel simulation support where team members can jump into the same project, work on the same project, and also discuss about the results or share the project internally as well. In the background, SimScale is AI powered. It not only reflects on the simulation level, but also there is a lot more operational automation is AI powered in SimScale. For example, before starting every run within SimScale, since you're running on cloud, you can get an estimation based on the complexity of the simulation, the mesh size, and also the runtime. This will already be useful when you're starting a complex simulation, and you can easily use this estimation for judging the complexity of the simulation. We also recently released the AI-based physics prediction, which can be used if you have an existing set of simulation data or you're trying to run a new set of simulation data. These data can be then directly used within SimScale to start predicting your new designs. The advantage here is within SimScale, you have all the data that you create in terms of simulation is already organized. The memory management is already taken care of. So you have a readily available data set for your training. And this can be done at any scale, right? Since we are on cloud, you're no longer limited to your local hardware, and you're also not limited to a definite set of simulations. For example, if you have a pump, which you see on the right, you want to do the entire pump curve, you don't need to start with one flow rate and then wait for the simulation to finish to start a new one. You can directly start a bunch of simulations at the same time. You can import your entire pressure curve or pump curve and start all the simulations in parallel. This way, you can easily scale your simulation capabilities and also save time and accelerate your design process. In terms of physics, SimScale supports flow, structural, thermal, and recently we have also released electromagnetics. So all these physics can be run within the same browser window. Okay, that's a quick overview of how SimScale is different from the other tools, but also the advantages of using a cloud-native tool like SimScale for simulations. I would like to start with a few examples from our customers and how they use SimScale for their own product development and design iterations. So on the left, you can see an air filter from Monodrot. It's a part of an air handling unit, and they use SimScale to reduce the power by simply making design changes, running simulations in parallel, and getting insights, detailed insights about their product, and driving the design changes effectively as well. The second and third examples here are from Elgin and CV Filtry, and they used simulations to understand the existing product type and find out regions where the failure might occur and improve that for better product development. The use cases that we have for today is similar to these cases and will give you a good understanding of how we can break it down, how we can make design changes, how we can actually predict insights and do it faster as well. Great. Now let's jump into the case study to actually see it in action, right? We have talked about like cloud native, any scale simulations, but picking up a typical workflow and running through it to see how you can increase your operational efficiency and also alongside improve your design as well. Let's suppose we have an air intake unit. And recently from our customers, we hear a lot of repurposing, right? The design industry is getting saturated, but also companies want to be sustainable. So they start looking into existing designs and want to improve in terms of efficiency or repurpose the existing design for your new product development. This is one such example where the base case has a single input filter, and then at the outlet, we have a single outlet. That's in the existing design. The task here is to repurpose this base model and make it suitable for multiple outlets. In this case, we're going to split it out with two outlets, which is going to be connected to two smaller turbines in the end, right? So let's say the management comes to the designer or the engineer and gives this task. And the first thing that you can do with SimScale is you don't need to actually have a detailed report that has all the simulation details and also the results that is produced with the existing product. All the management need to do is share the existing design details via SimScale's project link. So here we have the existing design details, and when I click through the design link, it takes me to the SimScale project, which has already been run by some of the engineers. And now I can see the results of the existing designs directly within a click. And this also helps you to organize and arrange your project details at the same place. In this case, I am within a project which is already run, and I've been redirected to one of the results for the existing project. And here I can see the animation is named as flow irregularities. So I already get a design insight and say that, hey, with one output, there is a lot of flow irregularities and also recirculation zones happening. And if I go to the next solution, I can see the regions where the velocity is less, which means there are dead spots or recirculation zones. And the task here is to reduce low velocity regions in the new designs. So as a designer, I immediately get access to the project that has been already run and the detailed design insights that has been stored within the project itself. The next thing shows a cutting plane with the flow distribution, and I can clearly understand with a single output, there is no uniform output of the airflow. And the task here is to use these existing designs and modify that for two output flows, right? We can focus on the dead spots, optimizing the flow characteristics, and also good distribution so that it gets separated between the two outputs. So now we have a project that I can start working on. For example, what I can easily do is take a look at the simulation that is already done. I can run through the simulation setup in detail and check out like what has been used as inputs. Let's say in this case, we have inputs from these shaders, and we have a velocity outlet at the end, which is connected to the turbine later down the stage. And to make a design change, a designer can actually work on the CAD using the existing CAD tool, and they can bring the CAD models within the same project. For example, I can either copy this project to my dashboard, or I can use the same project since it is shared with me. I can start importing new geometries. Imagine that we have imported 3 different designs, and we want to check which one is going to work better. It's clearly stated that we have a base design with veins and optimized. So optimized is going to be better, but let's suppose that we have 3 new designs that needs to be analyzed. For a design engineer, without prior CFD knowledge or simulation knowledge, this is going to be a huge task, right? Learning how to set up a simulation, what parameters to change, how can I get a successful simulation? How can I take a look at the results? All these questions are answered using a templated approach within SimScale. So within the shared project, I can already see I have the first simulation done. What I can easily do is simply duplicate the entire setup. And now I have a copy of an existing setup where I can rename and say, hey, I want to use the case with veins. And all I need to do is go into the geometry, change that to the geometry with the vein design. In this case, we already have a prepared geometry, but for minimal changes like changing the radius or diameter or shape of the existing equipment, you can do that within SimScale itself, which we'll quickly see in the second use case. For now, we'll focus on swapping the geometry using the same simulation template. Now, when I save, SimScale gives me a confirmation that all the CAD mapping was successful, which means I don't need to go as a designer from scratch setting up the simulation. I don't need to worry about the simulation type, the inputs, and the parameters. I simply change the geometry. All the boundary conditions are already preserved for me. Now I can directly go ahead, start a new simulation, let it run in the cloud, right? Here is the estimation of my simulation. I say it's fine, and then I can start the simulation. Right now, I've started a few simulations with the new geometry, and instead of waiting for these simulations to finish, I can also go ahead and do something in all the other simulations in parallel. For example, I have another design that I want to actually verify. So I can again duplicate this. I can go to the geometry and change it to my final design that I want to test. Here as well, we have a swap report stating that the CAD mapping was successful, so I can directly go ahead, start a simulation on the other geometry as well. And in terms of the results itself, so we can wait for a few minutes until the results simulations are run and the results are there. But for now, what I'll do is quickly jump onto the base case. And since I already have the simulations run, I can start comparing the results as well. So first thing, I can go into the simulation results of my base design. Let's say we pick up the final flow rate, one of the typical flow rates that we use. And once when the results load, I can also make use of the templated approach in terms of post-processing as well. So I'll give it a few seconds for the results to load. And as we mentioned, the way we support our customers is also unique. For example, let's say you didn't know how to open the results or how to change the boundary conditions. You can easily contact our support team using the chat, which lives within the platform, by simply sending us a message, and one of our team members can jump in quickly and help you then and there. This option is also extended if you want to share your project with our SimScale support temporarily. You can click on this button where one of our support engineers can jump in and see what is missing in your setup and guide you on how to actually make the simulation setup properly. Great. Now we have the simulation results of our base case with a split output here, right? All the results that has been used by our engineer in the previous project is replicated. And if you want to see the exact view or the results that you saw from the base case, you can also use manage views, where you can pick up one of the existing result state. This was newly released, where it takes up all the filters that has been previously used and reapplies that to your new case. For example, I can go ahead and say, hey, I want to use the exact post-processing from my base case. So I'm picking this from the project that I have, and I can apply the view easily. This will reload my results, but with all the filters and the results that was used in the base case. This way you have a complete comparison between your existing and the new simulation results, and you can start looking at the design insights. Great, I'll give it a few seconds here. Now we have the results on the screen. And the first thing I will want to look at is how the flow looks like within the system. From the base case, I can see that there is definitely an improvement in terms of splitting the results, but this is again using the exact geometry that we have and changing the outputs to two output system. If you want to compare how it was looking previously, you can easily compare the results between two runs. So I'm going to use the compare option and say, I want to see how it was looking in the base case. This can again load the results side by side, and you have a complete holistic view of how well the results have improved or worsened, depending upon what changes we make. And then you can start modifying the geometry and making the solution a little bit more efficient. So here on the left, we have the base case, and on the right, we have the single intake system. So it takes a few more seconds for the results to load. And once when both the results are on the screen, you have a completely synced view where you can start comparing the changes in the results due to the changes in the geometry that we have. So here you can see we had a high velocity draft and then a lot of recirculation, and most of the flow was going to the top section. And on the base case, we have similar flow up until the first filter, and then the flow changes and diverts because of the splitter that we have introduced to make it a two output system. Still, we see that most of the recirculation zones are preserved because we didn't make any design changes to the ducting or the filter itself, but we now have a base case where it can work for a two output system. If you remember, we started a few more runs with guiding vanes and also an optimized case. let's say we have the results for everything. Now I can go into the right side and say, I want to compare that with my case with the guiding vanes. In this case, you can directly see how we have improved over the base case with the vanes. And once when this loads, we can see the changes in the flow patterns. We can also compare what is improved, what is actually worsened. And finally, at the end of this session, we'll also look at the summary of what improvements we have made with the design changes and see which one is optimal. So here on the right, you can see if you compare the base case with the vanes, we have a definitely uniform flow at this region, and that helps spreading the flow in these both channels or both outputs properly, right? And if you quickly zoom in, you can see there is definitely a lot of pressure being lost at these sections, right? So this can be again highlighted by using an ISO volume to see where we have the low velocity regions. So in the base case, we have a lot of low velocity regions here in this section and also at the bottom output as well. With the vanes, it definitely improves. There is an improvement in terms of flow velocity here. These regions are gone or almost gone. And we also have a little bit reduced section at the bottom channel, which means there is enough flow going through the bottom. To further improve, you can actually go ahead and say, I want to compare that with my optimized case. And using this, you'll be definitely able to get a better understanding of how the design changes have affected your flow in terms of flow distribution, in terms of low pressure region or low velocity regions as well. That's a quick example of how you can change the geometry, use the same simulation setup, and start modifying your designs for better efficiency. And this can be actually replicated for multiple physics as well. In this case, we have just used air, and we are focusing on the pressure efficiency and the flow efficiency. But in case if you have an electronics cooling box where you want to see the position of your heat sink or position of your forced convection fan, you can also do the exact same workflow and use the base or existing design and start looking at design changes in terms of the flow distribution as well. Great, that sums up quickly the first use case. And in the second use case, we are going to do something similar where we take one of the base case and do some modification to the filter itself. In the first case here, you can see it's just repurposing of the existing design with two outputs. And sometimes what we hear from a customer is that depending upon the regions, geographical locations of your firm, the product might need different certifications. So in that case, you can have a base case from your parent configuration and start modifying it to make sure you can actually confirm with the certifications in your local area as well. Great. Now, once again, I'll remind, if you have any questions up until this point, please feel free to use the questions section, ask your questions, and we'll get them at the end of the session and answer them. If not, we can quickly jump on to the second case, which is a water filter. And here, again, my task is to actually look at the existing design. So this is one of my case with a filter that can actually capture 5,000 microns of debris. And the task here is to modify the filter to capture 3,000 microns, which means we need to capture finer debris, but keeping in mind that the flow rate should not change. So that's a twofold task where we need to capture the debris of finer size and also keep the efficiency or the flow similar to what we had in the base design. In this case, what I can do is quickly open the base simulation that I have and check the geometry. Seems like we have the 5,000 micron geometry, and to make sure it can actually capture 3,000 microns, I can quickly jump onto the first base geometry, edit a copy of the geometry that was existing in the project. By editing a copy, you will land in the CAD editing mode of SimScale, where you have basic operations like a delete, a face delete, move, extrude, or body delete, and some certain other operations that can be used. In this case, all we need to do is quickly change the dimensions of the filter by reducing the size of these porosity of the filter. So I'm going to select all the pores of the filters, and I can move the filter, let's say, to 3 millimeter or 3000 microns. This will change the geometry to affect for 3000 microns. Maybe I did that in the reverse, so I can go back to the move. I can say, hey, please don't increase the size of the diameter, but reduce it by introducing a negative sign. And when this is done, we have a new geometry that should have like a smaller pore size here. And the geometry which was edited here, I think there was something wrong with the setup, but once when you do the editing of your geometry, you can save this geometry as a new copy. And that's what we have done here. We have a geometry with 3000 micron pore size, and this can be now used to the simulation. And exactly following the same setup as the previous one, we can duplicate the base case, and I can go ahead and change the geometry to my new one with a modified pore size. Right here, if you make changes to the geometry in terms of the flow region itself, SimScale also wants you in the swap report stating, hey, some of your boundary conditions and assignments were not captured properly. So in this case, I can quickly run through all these assignments. Let's say my pressure inlet, and then I can select the face from the new geometry. I can do that for the outlet. I can also select the material properties from the geometry and a few result control items where I have captured the inlet and outlet velocity and the parameters here. If you're happy after setting all these partial mapping or failed mapping, you can directly go ahead, start a new simulation. Okay, we missed the pressure difference. Let's go back and set that up as well. And now I have my complete setup within a few clicks, and I can run the simulation on the new geometry. Right. Let's say we have run the simulations on this geometry. It's going to take a few minutes. Let's see how much it took for me. It took about like 45 minutes for this simulation. And I can go back to my post processor and check how the flow looks like. And most importantly, in this case, my task was to maintain the amount of flow that is in the base case. So if I go back, my base case with 5000 micron had a flow rate of about 11,000 liters per minute, which sums to like 0.19 meter cube per second. I need to make sure if my modified geometry produces the same amount of flow. So in the run that I have run with 3000 microns, I can quickly check my flow rate, and it looks like I have a reduced flow because the pore size have been reduced. So the task here is to actually reduce the pore size, but we have 10% plus or minus in terms of flow rate. So we need to check if this is beyond 10%. This comes around like 10 or 11% here. And as a designer, what I can do is if my geometry modifications didn't suit the criteria, I can go back, I can say, hey, I'm using the same diameter, but I would like to reduce the thickness of my porous media. So in this case, we have a thickness of about, let's quickly check the thickness of the pores. So by quickly measuring the edges here, I get a thickness of about like 0.009, which is 90%. Sorry, for the base case again, we have a thickness of about, let's say, yeah, 0.01 meters of thickness. My next step as a designer is to actually reduce the thickness to compensate the flow reduction in this filter. So I can easily do that by editing a copy again, going into the filter and moving this filter by, let's say, 10%. Once I move the filter, I have a new geometry which has a reduced thickness of the porous media, but a 3000 micron pore size. So now I can save this as a copy. And as I mentioned, I can again duplicate the same setup that I have. I can go ahead to the geometry and use my new 90% thickness of the filter. And in this case, since we didn't change too much in the geometry, the mapping was successful and I can start a new simulation here. Great. This is how you can quickly use the CAD mode to edit simple geometrical shapes or filters and start new simulations. And the interesting part is you can also go ahead and take a look at the results. And in this case, let's compare the base case with 5000 microns, 0.19, and I can go back to the other simulations with 10% reduction in thickness and 3000 microns, and quickly seeing it is about 0.172, and by back calculating that, it is around 9% of reduction in flow, which satisfies the criteria here. All right, that's in general a quick rundown of how you can use the templater approach, make changes to your geometry, and have a new product being simulated within a few clicks with the existing templated workflow. I'll quickly summarize this on this slide, but I'll also look for questions from the audience to answer here. All right, here is a quick summary. I took some time to actually pull out all the results that you saw from the 2D plot that we generate from simulations. And for the first case, we keep the flow rate constant. We want to check whether the changes from a single output system to a double output system affects the pressure drop and whether it is within the allowable limits here. So for the single output system, we had about 230 pascals of pressure drop. And for the base case, since we included the splitter, there is already some improvements in terms of pressure drop. We have about 200 pascals of pressure drop. And our criteria here is to actually range between 120 and 180 pascals. So we further went down, added the vanes and optimized the duct in terms of the smoothness at the corners, and finally ended up with a pressure drop of 171 Pascal, which satisfied the criteria here. This is an overall reduction in pressure drop of about 26%, but we also have repurposed the existing geometry for a new system which has like two output at the outlet. For the water filter, we took the existing case that was capturing 5000 microns of debris. We had an inlet pressure of 1.6 bar, which cannot be changed because for that to maintain the pressure within the system. And once we reduce the porosity size or the filter size for 3000 microns, we see a reduction in flow rate, which is not ideal. And this is about 10% of what the reduction of flow is allowed. So we made some few changes to the thickness of the porosity. With 90 and 95% thickness, we have a respective pressure, flow velocity of about 5 to 3%, and we can easily pick the 95% thickness because it is a good balance between the flow rate and also it can capture now 3000 microns of debris. That's the summary of how you can use SimScale to accelerate your design process in terms of operational efficiency, and in terms of scaling up your simulations and finding out the optimal results here. Thanks for listening, and the stage is now open for questions.
Hi, Ajit. Can you hear me?
Yes, hi, Kanchan.
Hello. Thank you for that awesome presentation. And we just about have time for two, maybe three questions, and I already have something coming in. So the first question is about setting up and running an experiment with multiple simulations at the same time. This is specifically referenced about running separate simulation with different velocities. So I think maybe you showed this during the course of the demo. So if you can just quickly like touch upon
Yes,
it again.
definitely. I can quickly jump onto the project. And as you can see in the project, I mean, instead of setting up one flow rate or one particular parameter in your simulation, if it's within the boundary conditions, what you can do is quickly go on to the boundary condition and use a parametric input. Here we have used a CSV input of different flow rates. Here, a 5 flow rate curve, and you can also add more. And when you apply and start a simulation, this doesn't start one simulation, but rather an experiment, which means it's going to run all the 5 flow rates or any number of flow rates that you have given as an input in parallel. So that's what you can see when you start an experiment. You have all the flow rates running in parallel. Yeah. Hope that answers the question.
Right, great, Ajit. And the next question is about the geometry with the veins. If SimScale can be used to optimize the angle of the curved veins in the ductwork with the aim of reducing pressure.
Yes, that's a good question. So if it is a simple change like this, changing the angle of the vein or changing the position of the vein, this can be done within this SimScale platform itself. So you can edit the copy that you want to modify. Now you can select the faces, or if you have brought the veins as a solid model, all you need to do is select the veins or the part that you want to modify and use one of the operations from the above, right? In this case, I don't have the solid body, but imagine that if you have a solid body of the veins, you can select all the veins, translate or even rotate the angle of the vein to a particular degree to optimize the flow. Hope that answers the question.
Yeah, yeah. Thanks so much, Ajit, again. And really, it's just about time for one last question, which is the last slide that you showed where you had pulled all the data.
Mhm.
So one listener wants to know exactly how did you pull this data out of the simulation, and if you can quickly touch upon running processing, specifically like how you can create an animation to demonstrate the flow.
Okay, that's a question
So
again.
basically CSV output and as well as post processing of the solution field.
Yes, thanks. Definitely. In terms of the outputs that SimScale can produce, first thing is the quantity itself that you're interested in, right? So for these cases, what I did is like I went into the flow rate that I'm interested in, let's say the last flow rate. And what I have done is before starting the simulation, I have set some result control item. These are exactly virtual monitors that you use in a physical testing. For example, I'm monitoring everything that is coming through the inlet and also at the outlet. And once when you set up a result control item, while the simulations are running, you can go ahead and take a look at the area averages here. So at the inlet and the outlet, all the variables are written out. In this case, I was interested in the total pressure. So I can easily go ahead into this 2D plot and pick up the value from here. And this is exactly what I have done to build the summary of the results that I have done. In terms of the result visualization itself, you can go into the post processor. And once when you're within the post processing environment, you can easily use some filters to take a look at the interesting results and also capture them in terms of a screenshot or animations directly from SimScale. I can quickly go through one such filter here. So let's say we want to see how the flow looks like within the system. What I'm doing is making a cutting plane right at the inlet and using that as a source for my particle trace on the top. So I can pick the face here. Let me clip the model. And now I can put the source points somewhere in the face and play with the parameters to make sure I cover the entire length and breadth of my intake system. And now you have the velocity streamlines, which are static, but you can already see the rotational component here and the recirculation zones. But to create an animation, you can change the representation to comets. This will give you a lot more information. And from the top, if you click on animation, you can click the play button, and that will start animating the flow particles. So now I can either take a look at that visualization on the screen, or I can go ahead and take a screenshot or record this animation as an MP4 or a zip file directly from SimScale. And once the animation is rendered, you can then go ahead and download to your local system. I hope that clarifies the questions about the post-processor.
Yeah. Thank you. Thank you, Ajit, for that descriptive answer. And as we have run out of time, we'll not be able to take any more questions, but I see a couple of more questions coming in as a follow-up. So if it's okay, we will reach out to you via email. Thank you all. Thanks for participating. Over to you, Ajit, to wrap it up.
Definitely. Thanks a lot for listening. And as Kanchan mentioned, we'll be going through the questions and replying your email. We also have a recording of this webinar available in a few days. So if you want to take a look back at what we have discussed today and the questions that we have answered, you can simply go on to simscale.com and you can open the webinar site and you can watch them on demand. If you think that this is interesting for you and you want to actually optimize one of your products in specific, then we are happy to talk with you. Please feel free to leave us a message at sales@simscale.com or contact@simscale.com, and we'll be happy to reach out and have a one-to-one session to understand your case and also run through or work through accelerating your design process as well. Thanks a lot for listening, and have a nice afternoon and evening to one and all who have joined here.